Hello class, we're in section 3.10 using intervals for hypothesis testing. So in inferential statistics there are two areas, point estimation and interval estimation for a population parameter, and hypothesis testing. Now recall in section 3.9 we learned how to compute and interpret a point and interval estimate for the population proportion. The point estimate was just the sample proportion p-hat, and the confidence interval gave us an interval of numbers around our sample proportion. So recall that for all data, we break it up into qualitative data and quantitative data. And regardless if it's qualitative or quantitative, there is a sample size n, meaning how many individuals were in your sample. For both, little n is the sample size. For quantitative, we can summarize the data with a numerical summary for quantitative data called the sample mean. And we can also talk about the standard deviation S that talks about the typical distance any one data value is from the sample mean. Similarly, for qualitative data, you have a certain number of individuals in your sample, that's n. X is going to summarize how many of those individuals had the particular quality you were looking at. And p-hat is just a different way to summarize that. By taking x divided by n, you can find the sample proportion of those n individuals that had the quality or trait you were looking for. Now in this section, we're going to be using a confidence interval to test a hypothesis about the value of the population proportion p. So many times we collect sample data to see if a parameter has changed from some previously stated value. For example, it is claimed that 15% of the population smokes, but you get a sample where the sample proportion p-hat is 20%. Notice 20% is larger than the claimed value of 15%. Is it just a random sample fluctuation up, or is it evidence that the population proportion is now greater than 15%. Here's another example. A company claims that 40% of Americans use their brand, but you get a sample where the sample proportion is 38%. Is this just a random fluctuation down, or is it evidence that the population proportion is actually less than 40%? So these are the type of questions we want to answer with hypothesis testing using a confidence interval. Now in general, there are several ways to answer these questions. There's the classic approach. This was really an old way of testing hypotheses that involved tables before we even had computers. That has pretty much disappeared, but some people still do the classical approach without computers. There's the p-value approach, which is done in other statistics courses, but we're not going to handle that particular approach. And then thirdly, there's the confidence interval approach. And since in section 3.9 we went over a confidence interval estimate for a population proportion, that's the approach we're going to be using to answer the question about whether a sample proportion was just a random fluctuation up or down, or if the sample proportion really is evidence that the population proportion has went up or down. So we're going to be using the third option, the confidence interval approach. So in the previous section, we just learned how to compute confidence intervals. So what we're going to do now is we're going to take sample data and we're going to use one prop z-interval, provided that we have the assumption satisfied, to find a confidence interval surrounding our sample proportion. And we're going to compare the claimed value for the population proportion p and our confidence interval for the population proportion p. So in this approach, we're going to compare the values of the confidence interval to the claimed value of the population parameter. So to begin with, well, you've got to compute a confidence interval for p, and that was covered in section 3.9, where we had the 5-step process and we had the word panic to help us out. Once you have the confidence interval, you have 3 different cases. If the entire confidence interval is above the claimed value of P, then there's significant evidence that the population proportion P is actually bigger than what they've claimed. If, on the other hand, the entire confidence interval is below the claimed value of P, there's significant evidence that the parameter is actually smaller than what is claimed. So here, if the entire confidence interval is above the claimed value for P, then there's significant evidence that P is bigger. If the entire confidence interval is below the claimed value of P, there's significant evidence that the value for the population parameter P is smaller than claimed. The last case, if the claimed value of P is actually inside the interval, there is not evidence that P has changed from what they have claimed. Okay? And so in that particular case, you would chalk up your sample proportion being different just because of random fluctuations due to sample fluctuations. So let's go ahead and look at these 3 cases. The entire confidence interval being above the claimed value of P, the entire confidence interval being below the claimed value of P, and where the claimed value of P is within the confidence interval we computed. Let's look at some examples of those cases.